A novel flow system that I conceived here at RPI is being tested aboard the International Space Station. We're going to be looking at the fibrillation kinetics of a particular protein, in this case insulin.
When you have fluid motion, it imparts a shear stress, and that shear stress increases the rate at which protein goes bad and turns into fibrils. Amyloid fibrils are the hallmarks of various proteopathic diseases, Alzheimer's, Parkinson's, other diseases as well.
Being able to do the experiment in microgravity allows us to have a fairly good size drop that makes measurements easier, it makes the problem a lot more tractable. This lack of gravity means that there's no need to hold the liquid with a dish. So the idea is you have a ball of protein that's constrained from floating around in space by touching a thin ring, and then a second ring can touch it and rotate. And we can study the effect of hydrodynamic stress. It's called a ring shear drop.
If this experiment is successful, there are different avenues where you can actually apply this. So you can not only use this to understand what happens to the diseases in the human body, but also really use it as a platform to make drugs in space.
More and more people are realizing fluid dynamics is not a secondary issue. It might be a primary issue physiologically. Our project is funded by NASA Marshall Space Center.
They came here to witness and certify that the samples that we're making are what they're supposed to be.
They set up a station, a room in the basement of JEC, so that we can run the experiment in real time and in fact send commands up to the module. Getting the ring shear drop to work in space, that's the first step. The next step would presumably be switch proteins that's in Alzheimer's.
The fact that we're taking something on Earth that we can't really study on Earth and then having to go to space in order to rule out some variables is incredibly interesting, and more interesting is that it's never been done before.